We're back online. Now we're going to be getting a presentation on the cutting edge in human feedback enabling development of frontier multimodal LLMs. What a mouthful. With us is Manas Talukdar, and Manas is a senior leader in enterprise AI and data infrastructure. He has over 17 years of experience. He has held just a series of leadership roles at both startups and large public companies. He's played a pivotal role in enabling the go-to-market strategy for these products. Um, so Manas has contributed significantly to the world's leading industrial process data sorry about that. He is a key role in shaping the way that industrial data is being processed and engineered in modern platforms. Currently, he's serving as a director of engineering at Labelbox, where he oversees a big part of the development of a data-centric AI platform. So, with that, Manas, the floor is yours.
All right, thank you, Joaquin, for the introduction. So, hi everyone, my name is Manas Talukdar. As Joaquin said, I'm Director of Engineering at Labelbox, an AI startup based out of San Francisco. I've been in the industry for almost 2 decades and have extensive experience working on artificial intelligence and data infrastructure. I'm excited to be giving a talk at the Swarm AI Expo about the cutting edge in human feedback, enabling development of frontier multimodal LLMs. So we'll start this talk by setting the context through a short overview of generative AI and LLMs. We'll discuss the motivation for human feedback in generative AI, mechanisms for human feedback, and the latest research and applications in human feedback techniques. We will dive a bit into industry trends, specifically drawing on my own view from what I consider to be a front row seat. Finally, we will end the talk with some points on what the future might look like in this domain. So let's talk about generative AI for a little bit to set some context. So unlike classical or traditional AI, which deals with things like classification, prediction, and decision making, generative AI is about creating new things. It is about creating new images, new music, new text, new videos, and so forth. Generative AI is about creating new things that have never existed before. And there are now services based off of large language models that power and provide easily accessible interfaces and APIs for these various generation tasks, whether it's text, image, code, and so forth. So let's talk about large language models. So large language models are deep learning algorithms trained on massive data sets to excel at a variety of natural language processing tasks. Their primary function is to predict and generate human-like text. Uh, Most modern LLMs utilize the transformer architecture, which allows for efficient processing of sequential data. The large in LLM signifies the immense scale of these models, encompassing the sheer number of parameters ranging from millions to hundreds of billions, the massive size of the training data sets, and the significant computational resources required for training. This typically involves a pre-training phase on vast amounts of text data, followed by fine-tuning for specific tasks or domains. Obviously, with multimodality, we have LLMs which can not only generate human-like text, but also generate images, videos, audio, and so forth. So why human feedback? There was a New York Times article a few months back that highlights a growing challenge in the field of large language models, the need for fresh, high-quality training data. As LLMs consume existing data sets at an unprecedented rate, the race is on to find new knowledge instigators, sources of original, valuable information. This high quality training data is rapidly becoming the key differentiator between LLMs, particularly for specialized fine tuned models. It is also relevant to mention that if you, for example, you ask a very generic question to some of those LLMs out there, whether it's from Anthropic or OpenAI or Google or some other provider, a question like, say, who is Elon Musk? It'll give you an answer, and you'll be splitting hairs to find the difference between the answers. That's because these LLMs have all been trained on pretty much the entire internet. And this is why they are now looking for new data to train their models. To truly unlock the potential of LLMs across various domains and maintain their accuracy and relevance, the quest for new data needs to operate at internet scale. This demand has fueled a surge in the need for specialized skills in data annotation, curation, and generation, reflecting the critical role human feedback plays in shaping the future of AI. In this talk, we will discuss some of the mechanisms of human feedback, including human in the loop, reinforcement learning from human feedback, direct feedback, and direct preference optimization. So let's talk about human in the loop. Human in the loop is training large language models, and that extends far beyond the popular technique of reinforcement learning from human feedback. It's a comprehensive process demanding human intervention at every stage, encompassing data collection, model training, evaluation, and refinement. Humans are essential for creating and annotating vast amounts of training data, crafting diverse prompts, generating desired responses, and classifying model outputs for accuracy and alignment. This human feedback loop is crucial for model evaluation and error analysis, allowing developers of LLMs to identify biases, inaccuracies, and limitations. Through iterative cycles of human feedback and model adaptation, LLMs can achieve higher levels of accuracy, fluency, and alignment with human preferences, ultimately leading to more reliable and beneficial applications. Reinforcement learning from human feedback is a very powerful and perhaps the most popular technique for aligning large language models with human preferences. Starting with a pre-trained LLM, RLHF leverages human feedback on model outputs to guide the learning process. This feedback can take various forms, such as ranking different model outputs, providing better demonstrations, or directly assigning scores to indicate output quality. This feedback is used to train a reward model that runs to predict human preferences, that is, how much a human would like a particular model response. Finally, the LLM is fine-tuned using reinforcement learning, aiming to maximize the rewards provided by the training provided by the trained reward model. The LLM generates responses and the reward model evaluates their quality. This feedback, often represented as a reward score, guides the LLM training process through a technique called proximal policy optimization. The LLM iteratively adjusts its parameters to generate responses that maximize the reward signal. And by reward signal, we mean the responses the reward model predicts that human will prefer. So this approach yields several advantages, including better alignment with human preferences, improved performance on subjective tasks, and potentially mitigating harmful outputs. However, challenges remain, such as potential biases in human feedback, which will percolate onto the LLM itself, and then reward hacking by the LLM, and of course, the logistical difficulties of scaling human evaluation at internet scale. Direct feedback in LLM training involves human evaluation to provide explicit guidance, surpassing the limitations of purely data-driven approaches. Several types of feedback exist, including ranking multiple model outputs, providing numerical scores, making comparative judgments, and offering free-form text explanations. The process begins with prompt generation, followed by model output generation based on the prompt. Human evaluators then assess these outputs according to predefined criteria, followed by their chosen type of feedback. This data is aggregated and used to further fine-tune the LLM, leading to several benefits. These include improved performance on downstream tasks, better alignment with human preferences and values, and increased model explainability through the integration of human reasoning and logic. Then direct preference optimization is an alternative approach to RLHF for training LLMs that simplifies the process by eliminating the need for a separate reward model. DPO directly leverages human feedback through pairwise comparisons, which is the key differentiator with RLHF. In pairwise comparison, annotators indicate which of two model outputs they prefer for a given prompt. This preference data is then used to train the LLM by minimizing a loss function that encourages the model to generate outputs consistent with human preferences. This iterative process involves collecting human feedback on new model outputs, updating the model based on the collected preferences, and repeating. The simplified model training process, devoid of the complexities of a reward model, leads to improved alignment with human preferences, potentially fostering more robust and scalable LLM training methodologies. Let's talk a little bit now about some of the cutting edge in human feedback driving frontier LLM development. So EvalGen is a novel framework developed by researchers at UC Berkeley. It tackles the challenges of aligning large language model assisted evaluation with human preferences. Recognizing the limitations of purely automated metrics, EvalGen leverages human feedback to fine-tune the evaluation process. The evaluation framework provides automated assistance in two key areas: generating relevant evaluation criteria and implementing these criteria as executable assertions. So instead of relying solely on humans for these tasks, EvalGen proposes candidate implementations and asks humans to grade a subset of LLM outputs based on the proposed criteria. The human feedback loop is crucial, allowing EvalGen to learn which implementations best capture human judgments and ultimately select those that demonstrate superior alignment with user-provided grades. The iterative approach enables EvalGen to refine its evaluation process, resulting in more accurate and human-aligned assessments of LLM performance. We'll now talk about OpenRLHF. OpenRLHF is an open source framework designed to streamline reinforcement learning from human feedback training for large language models, even exceeding tens of billions, say 70 billion parameters and so forth. Seamlessly integrating with Hugging Face transformers, it leverages powerful technologies like Ray, VLLM, and DeepSeed to ensure efficient training. OpenRLHF introduces key innovations, including scheduling, proximal policy optimization, implementing several other optimizations, alongside support for cutting-edge other technologies. This framework surpasses OpenRLHF solutions by enabling larger model sizes, offering advanced training techniques, which is a key offering from RLHF, and readily implementing diverse alignment algorithms. By tackling the complexities of multimodal coordination inherent in RLHF, OpenRLHF provides a scalable solution, paving the way for the development of increasingly sophisticated and aligned LLMs. Then we'll talk about constrained generative policy optimization. This is a very recent development in this domain, probably came out like just a few months back. So CGPO introduces a novel multi-objective RLHF treatment strategy where each task is managed individually with customized optimization settings. This approach includes task-specific reward models, mixer of judges, and optimizing hyperparameters. This new multi-objective RLHF strategy employs a mixer of judges system featuring novel optimizers like calibrated regularized policy gradient, constrained online direct preference optimization, and calibrated regulated reward ranking fine-tuning. These optimizers leverage a combination of rule-based and LLM-based judges to evaluate LLM outputs for adherence to constraints across diverse NLP tasks. This approach offers several advantages, including minimal hyperparameter tuning, seamless integration with existing post-training pipelines, implying plug-and-play compatibility, and effective mitigation of reward hacking behavior. So one of the things we talked about in RLHF was one of the potential issues was reward hacking. Obviously, this technique mitigates reward hacking. Another very recent development that came out of academia in this domain is called Revis Eval, which essentially introduces a novel two-stage evaluation process for language models that significantly improves on traditional methods. So first, it leverages prompt engineering and the power of LLMs to generate response adapted references tailored to each individual model output. Then using these dynamically created references, Revis Eval conducts a more nuanced and consistent evaluation of the responses. This approach minimizes bias towards specific answer styles, thus taking into account human biases, better captures subtle differences in reward models, and ultimately achieves greater alignment with human judgments compared to just using static references. So now we'll discuss some of the examples of how human feedback is driving uh, developments, driving concrete LLMs and so forth in this domain. So RLHF 18K is a novel data set designed to enhance the training of large language models for image generation tasks. This data set comprises 18,000 images paired with rich human feedback going beyond simple ratings. The feedback includes marked regions deemed implausible or misaligned with the corresponding text prompt, along with annotations pinpointing misrepresented or missing words. Furthermore, each image receives 4 fine-grained scores: large plausibility, text image alignment, aesthetics, and an overall rating. This rich feedback is then leveraged by the rich automatic human feedback model to improve image generation in two ways: by curating high quality training data for fine tuning generative models, and by creating heat map based masks to guide the in-painting of problematic image regions. Notably, the improvements facilitated by this dataset generalize beyond the models used to generate the original dataset images. So, thus demonstrating its potential to enhance diverse image generation models like Muse and so forth. Another example is in video generation models. So two recent approaches leverage human feedback to enhance video generation models. Instruct Video, one of the ideas discussed in the slides, focuses on directly instructing diffusion models using human preferences by incorporating human feedback into the training process. Instruct Video guides the diffusion model to generate videos that align with specific instructions and desired outcomes. Conversely, Video Score, the second example in this slide, aims to build an automatic metric that efficiently simulates fine-grained human feedback. So this metric, applicable to various tasks, including RLHF, can evaluate and guide video generation models without the need for constant human intervention. And some of the examples we discussed for constant human interventions previously include EvalGen, RLHF, and so forth. So while Instruct Video relies on direct human feedback while training, Video Score seeks to automate the feedback process, potentially offering a more scalable solution. Then the next example we discuss is in language translation for LLMs. So it's called multilingual preference optimization. So multilingual preference optimization is a novel approach designed to align large language models with human preferences across a diverse set of languages, particularly those underrepresented in dominant data sets. So think about, say, a language that's not English or Chinese, or one of the more commonly known world languages, a language which is not as commonly spoken or known, say for Sanskrit, for example. By leveraging a multi-language reward model, MPO captures both universal and language-specific aspects of preferences, facilitating effective cross-lingual transfer learning. Cross-lingual transfer learning is a common technique used in machine learning, which is now being adopted for LLM development as well, particularly for language translation LLMs. So this approach allows for strong performance even in low resource languages with limited training data. Further enhancing its adaptability, MPO also utilizes a language-specific value head to fine-tune preference alignment within each language. Findings indicate that MPO significantly outperforms existing models in generating high-quality text aligned with human preferences across multiple languages. Another related mechanism is called multilingual alignment as preference optimization, or MAPO. I will direct listeners to the relevant paper for more details. In the interest of time, we will not cover MAPO in this talk. Now, let's talk about a little bit from my own experiences in this domain. So, training LLMs demands a confluence of high quality data and cutting edge techniques. Crucially, this data must be accurately labeled, forming a ground truth for the model to learn from. Uh, and even more importantly, what's happening now is training necessitates specialization. If you think about some of the specialized models that are coming out, or maybe a company wants to fine tune their baseline trained LLM for some specific tasks, like say for the medical field, where some company wants to develop an LLM which wants to be able to infer from X-rays, for example. So that demands very high quality data, ground truth label data of X-rays. And for that, for example, demands that we have cardiologists who come in and annotate these X-rays to provide training data or fine-tuning data for these LLMs. And that is a definite direction that the industry is moving towards. And another example could be satellite imagery for atmospheric analysis, or text in language as diverse as Sanskrit, German, or Arabic, where the data must align with the intended application. And then human feedback collected at scale and with speed is another important component. Methodologies like RLHF, DPO, are fueling the development of increasingly powerful LLMs, enabling them to better understand and respond to nuanced instructions. This push towards more specialized, multimodal, and capable LLMs hinges on the ability to acquire, annotate, and leverage vast and varied data sets. I also mentioned earlier in this talk that most of the LLMs out there, they have been trained on the entire internet, which is why their responses are pretty much the same. You'll be splitting hairs to find the difference on some generic question. So the need for ground truth label data for specialized use cases has become even more dire. And this is even more important in the medical field because, as a previous speaker mentioned, the margin of error for LLMs in the medical field is very low. So the ability to provide high quality ground truth label data is extremely important here. So as I mentioned in a previous slide, as a New York Times article also highlighted, the future of training LLMs on overcoming the growing scarcity of high quality data. I was at a conference a few months back, and the head of AI infra at Facebook openly said that we have basically run out of training data and we need new data to train our LLMs. So one promising avenue lies in the use of synthetic data powered by LLMs themselves to supplement real world examples. However, we have to tread carefully here because this approach needs robust evaluation mechanisms. And it is here that human feedback remains essential. So we can envision a future where LLMs acting as judges or through sophisticated reward models are trained to align with human preferences and identify the most valuable synthetic data for training their successors. And I'll give an example. So some months back, NVIDIA released their Nemotron models. And in their technical report, they mentioned that they had actually used synthetic data to train their LLMs. In fact, very recently, this is just some days back, I recall Tencent released an LLM and they trained a big part of that LLM using synthetic data. So it is given that synthetic data is going to become more and more important, but we have to very carefully evaluate the quality of the synthetic data. And this is here where human feedback, human in the loop techniques can come into play. So these techniques, coupled with continued rapid innovation and human feedback mechanisms, will be crucial to propel LLM development in the foreseeable future. So that's all it for my talk. Any questions?
Thank you, Manas. This was a very deep technical dive into all these things that you're working on a day-to-day basis, particularly in developing the platform that you're working on, right?
Yeah.
So what are some of the use cases that you're seeing, and what are some of the constraints or challenges that they're encountering in employing multimodal AI?
So there's two parts to that question. Let's address the second one first. So the constraint we're seeing is the growing limitation of training data, particularly high quality training data. So we are seeing an extremely dire need in the industry for high quality training data. And because, as I said, the AI labs, and by AI labs I mean the large companies developing these massive large language models, they have run out of free data to train their models, and there is a dire need for high quality training data. That's one. Secondly, they are also looking to have their LLMs go be in the post training phase, beyond the baseline training, to specialize for certain use cases, whether it's a specialized codex model, whether it's a specialized model for medical use cases, whether, as I said, the example being able to infer off of x-rays, or a specialized model for language translation. And there is also a very dire need for high quality training data there too. So
So what?
that's, go ahead.
No, you're going to answer the first part after, right after. I have a follow up for this though.
Right. So the use cases are, as I said, say an LLM which wants to read satellite imagery and infer off of that, or an LLM that wants to infer off of chest X-ray images and figure out what ailment a patient might have. Or we are seeing a lot of use cases in the industry where companies are developing LLMs for language translations. Now, what is given is that for the initial baseline training phase, multimodality is a must. All of these LLMs are being trained for multimodality, and then the specializations happen. Okay, this post training phase kicks in where the specialized use cases come into play.
Okay. Um, very, very interesting. Are you guys working on developing some sort of mechanism to create a mechanical Turk in the implementation areas that you have? A way to empower the users, the stakeholders, to be able to annotate data as they use and encounter new situations or scenarios in their day-to-day work?
Absolutely. So at my current workplace at Labelbox, we also support self-serve. So we not only work with enterprises, we not only work with AI labs, the large LLM developing companies, but we also work with uh, self-serve customers who can actually come into our platform. They can annotate data. They can generate training data off of their own.
So how does that work? Say, for example, I run a hospital and I want you to service the radiology department
Right.
because I want to have a better detection, proactive detection of cancer.
Right.
So there's open data sets I can take that are, let's just say for simplicity's sake, reflect the local population demographics.
Right.
So it's relevant data. I use that to train or enhance a open source model that is not going to put me out of business with the amount of money that it costs. And then I come to you and I say, we've gotten a limited amount of success out of this, and it's supporting the operationalizing of this AI for detecting cancer. How can we get better?
So there's multiple ways we can help there. We allow supervised fine tuning on our platform off of foundation models. So that's one mechanism. Second mechanism is that you may have, say, for example, in your example, the hospital might have, say, ontologists readily available who can actually do these annotation tasks, but they need a platform to be able to do that. So we support that as well, where you bring your own workforce. The third option we support is that we provide the specialists. So we may be able to provide those ontologists, we may be able to provide those medical professionals who can actually do those annotations of those images and so forth, and provide those training data for you.
And what has been some of the overall results from the work that your organization is performing?
Well, the results have been really good. So, as I said, we are working with a lot of AI labs to help drive the development of multimodal LLMs. And for example, I'll give you some examples. So we have customers, for example, it's a robotics company who used our platform to develop a model for uh, for doing more precise remote surgery. We have a big enterprise who used our platform to develop a model which enables better detection of weeds in and so forth. So we have a lot of, not only AI labs, we are working with specialized enterprises as well for particular task-specific custom model development too.
The interesting part about the work you're doing is it could be applied to anything:
Exactly.
agriculture, healthcare, yeah, anything.
Any field, right?
Excellent. Well, thank you very much for that wonderful presentation. I hope everybody got value out of that. We're going to take a brief intermission, about 20 minutes or so. So grab a cup of coffee, a cup of tea, and we'll be back with the panel. Thank
Thanks,
you.
everyone. Thank you, Joaquin.